let's talk about determinants. Okay, of course, the catch here is we are not talking about determinants for matrices over a field, but rather over general rings. Okay, so recall, so let me make the following assumption that let R be a commutative ring now. Let R be a commutative ring. Recall that means in our notation, if I look at what we called R op, the identity map, it sends every element to itself. This is an isomorphism of R to R op, right? Because the operation in R op is just the product in the reverse order, but since R is commutative, AB is the same as BA. Okay, another way of saying it is therefore that the identity map from R to R op is an isomorphism. Okay, so of course, why do I want to bring in R op and so on? So recall from last time we talked about how to think about endomorphisms of free modules. So a homomorphism from Rn to Rn is really given by an n cross n matrix, and this matrix we said should correctly be thought of as an element of R op, but since R is commutative, I can replace R op by R, right, because of this fact that I just said. This is true for R commutative. Okay, and recall how the map was defined. Given a homomorphism phi, to that homomorphism we could pick the standard basis of Rn, what we call the EIs, and you just apply phi to EI and write out the entries, write the answer as a linear combination of the EIs again, and write the entries in the ith column, right. So this we call the matrix of the homomorphism phi. Okay, so now what we want to do is to talk about automorphisms. Okay, so what's an automorphism? Remember that just means it's an invertible endomorphism. So an automorphism of Rn just means it's a map phi which also admits an inverse. Okay, so phi is said to be an automorphism if there exists a map psi, which is again an endomorphism of Rn, such that phi composition psi is the same as psi composition phi, and this is equal to the identity map of Rn. Okay, so this is the usual notion of automorphisms. It's an isomorphism from the module Rn to itself. Okay, now here's the important thing, that if I have so the question now really becomes, every endomorphism is associated to a matrix, but what can I say about automorphisms? What do matrices of automorphisms look like? Okay, and so here's the main proposition which answers that question, and we'll say a little bit more about this. So the proposition says that phi is an automorphism. So same notation as before. So map from Rn to Rn if and only if the matrix of phi has the following property. Look at the matrix of phi, n cross n matrix, if and only if the determinant of that matrix, well, what is the determinant? Well, we'll come to that in a minute. If and only if the determinant is a unit of the ring R. Okay, so recall the unit means it's an invertible element of the ring R. Okay, so let me, before actually getting into the proof and explaining more about this, let's just do an example. Suppose I take the ring R to be Z, okay, and suppose I take a matrix A which is say 2 0 0 1, very simple diagonal matrix. Well, the determinant means the usual thing, you sort of know how to take determinants of matrices by using the formula, you expand along rows or columns and so on. So in this case, if I have 2 0 0 1, the determinant is just 2 times 1, which is 2. But observe, if I think of this as being a matrix with values over the underlying ring Z, then 2 is not a unit, it's not invertible in Z. Okay, it's of course invertible if you think of it as an element of Q, the rational numbers, or R, the real numbers, or complex numbers, and so on, but it's not a unit in Z. Okay, so the point is, so let's just try and so this is what I mean by saying that the determinant must be a unit of R. So let's first as a preparatory step to proving this proposition, let's first convert this statement about automorphisms into the corresponding statement about its matrix. So observe, phi is an automorphism means there exists an inverse psi. This is an automorphism. It's the same as saying there exists psi from Rn to Rn such that, as we said, phi composition psi is psi composition phi is the identity operator on Rn. But now we also looked at what does this mean in terms of the matrices. So I said that the map which associates to each homomorphism its matrix, that map is a ring isomorphism, right? In other words, composition of maps goes to product of matrices. I mean, if you were over a non-commutative ring, you would have to take R op, but over a commutative ring, it's just the same as R itself. So phi composition psi, so let me take the matrices on both sides. This is the product of the two matrices of phi and psi. On the other side, it's the product of the matrices psi and phi. And the matrix of the identity operator is just the usual n cross n identity matrix, okay, with ones on the diagonal. So remember, 1 is now here an element of the ring R. Okay, so I think of the multiplicative unit of the ring R. Okay, so this is the n cross n identity. So now what does this mean? And conversely, if suppose I could find corresponding to the matrix of phi, if I could find another matrix such that the product gave me identity in both directions, then I could just take psi to be the homomorphism, the endomorphism whose matrix is that given matrix. Okay, in other words, it's sort of easy to see because everything is you can identify homomorphisms with you can identify endomorphisms with matrices, n cross n matrices. So I can sort of reverse this chain of equations. Okay, if and only if there exists a matrix of psi such that. Okay, so what does this really mean? It says that to understand when phi is an automorphism, it's enough to understand when the matrix of phi has an inverse. Okay, so this matrix here is the inverse of this matrix phi. Okay, so therefore phi is an automorphism is the same as saying the matrix of phi is an invertible matrix. Okay, it's got a matrix inverse. But now where is this happening? This is in the space of all n cross n matrices with entries in the ring R. Okay, so recall that this itself is a ring, the ring of matrices with entries in any ring R itself is a ring, and we are saying that this matrix phi has to be an invertible matrix in that ring. It should be an invertible element of that ring. Okay, so what we need to therefore do is really the following proposition. So what we need to prove is really the following fact, that when is a matrix invertible? So a matrix A in the ring of n cross n matrices is invertible if and only if its determinant is a unit. Okay, so this is really what our proposition amounts to. I have just converted everything from homomorphisms to matrices. Okay, so first thing is, what is the definition of the determinant? Well, it's the most obvious definition. So let's just convince ourselves that even if A is a matrix with entries in some commutative ring R, I can still make sense of the determinant of A. So how do we define the determinant? Well, we have the usual definition where we expand along the rows and so on, but in one shot, if one sort of wanted to write it, here's how we usually write this. We say take all permutations of Sn, permutations in Sn, permutations of 1 through n, and do the following. Let's look at the, okay, I'll call this epsilon of sigma. This is a sign, so maybe we'll just write it as a sign. So remember, we have the sign of a permutation, which is +1 if it's an even permutation and -1 if it's an odd permutation. So I take the sign of sigma, and then a 1 sigma of 1. So first row, sigma 1th column, take the element in the second row, sigma 2th column, and so on. So I take this product a n sigma n. Okay, and this is sum overall sigma n Sn. Okay, this is the usual definition of the determinant in terms of the expansion along rows and so on. So what this amounts to is like saying, if I have say a 3 cross 3 matrix, so I take this from the first row, maybe this from the second, this from the third, or you know, I could take this from the first row, I could take this from the second row, this from the third row, and so on. So I sort of run through all the possibilities of choosing one entry from each row and each column. So I have to choose n exact entries. I take their product and then I multiply by the sign. There is always a sign involved in the determinant expression, and this sum is exactly the determinant. So observe that this makes perfect sense over any commutative ring R. Okay, so this, firstly the answer lies in R because it's a product of elements from R, and the commutativity of the ring is required so that I don't have to keep track of the order in which I mean, you could conceivably define this for non-commutative rings, but it wouldn't have the nice properties that you expect of it. Okay, so a commutative ring, at least the nice thing is that you don't need to keep track of the order in which you multiply, right? You take something from the first row and then you take something from the second row, or you do it in the other order. Okay, so this will ensure that the nice properties of the determinants remain. For example, if you interchange two rows, the value of the determinant becomes a negative. Okay, so things like that we want to happen. That will only happen if you assume that the ring R is commutative. Okay, so we only define it in that case. Okay, great. So observe that the order is immaterial and the definition makes sense. It gives me an element of R, and the other main reason for doing this, of course, it has all the usual properties that we expect of a determinant. Okay, so for example, so I've already said it belongs to R. So I'll just reiterate that the determinant of A is an element of the underlying ring R. Second property, if you interchange two rows or columns, if two rows or two columns are interchanged, the value becomes negative. Minus of the original determinant. Okay, that's the second property. Property 3, if I I can do this recursive expansion along rows or columns, can recursively expand. So this is just the usual way in which we compute it. And that's just another way of saying that it's the same definition. And the fourth property, which is arguably the most important, which says that if I take the product of two matrices, the determinant of the product is just the product of the determinants. Okay, this is not so easy to prove from the definition. Okay, it requires a little work, maybe using the elementary row operations and so on. And this is something we'll come to later. So for now, just think of this as a black box. So just accept this formula. It works in some sense for the same reason that it works over a field. It's just a formal property of multiplying two things out and so on. Okay, so we will give a proof of this during the maybe one of the problem sessions. Okay, so let's go back to what we want to prove. So we really want to say that the determinant is a good way of detecting when a matrix is invertible. Okay, if the determinant turns out to be a unit in the underlying ring, then the matrix is invertible, and conversely. So let's prove this statement. So first observe that if A is invertible, so that's the easier half of the implication. So if A is invertible, in the matrix ring, what does that mean? There exists a matrix B such that AB equals BA equals identity, and now we use the property of determinants, that determinant of AB is the determinant of A times the determinant of B. So this is det A det B, and the determinant of the identity is just 1. It's just the product of the diagonal values. And so this implies that, so now recall, everything is in the ring R, all this action is taking place inside the ring R. This is a ring element, this is a ring element, right? So what that means is that the ring element det A has an inverse in the ring. There exists an element in the ring such that their product is 1. Okay, so this is exactly saying that determinant of A is a unit in the ring R. Okay, so that's this one half of the proposition. Okay, now let's prove the converse, that if the determinant is invertible in the ring, then the matrix A has an inverse matrix. Okay, so let's do the converse now. So if determinant of A is a unit. Okay, so what does that mean? In other words, I can talk about an element called det A inverse in R. Okay, there exists an element which is the multiplicative inverse of the determinant. Okay, now given this, I need to produce an inverse matrix for A, and this is I mean, if you sort of just think about it for a minute, the clue for how to do this really comes from the formula for the inverse that one uses in the usual case of fields, which is, how does one construct or compute the inverse of a matrix A? Well, let me call that B. This is what we usually do. We say it's 1 by the determinant times what's called the adjoint of the matrix A, right? The transpose of the matrix of cofactors of A. So this is nothing but so our usual formula. So let me put it within brackets over a field, within quote. So we would write it like this: 1 by det A times the matrix called adjoint of A, which is transpose of the cofactor matrix, right? This is the usual formula. Now what we have to, I mean, this is over a field in general, but what we have to realize is that this formula actually makes perfect sense over any ring, okay, provided I can make sense of 1 by det A. Okay, so that's exactly what I have assumed, that det A inverse is an element of R. Okay, so let's try, just as a guess, just try making the same definition. So we'll say B, let's define B like this and hope that it has the right properties. Okay, so now let me say B should be an element of, where should B lie? It should be an element, it should be an n cross n matrix with entries in R. Well, I will do the following. I will use det A, it's a ring element. The inverse of det A is, again, it's assumed to be assumed to exist, element of R. So I will take this element of R and I will multiply it by the adjoint matrix. Now what is the adjoint matrix? Does that make sense over any ring R? Well, it's the matrix, the transpose of the cofactor matrix, right? The adjoint of a matrix is defined like this. This is, you take the cofactor matrix of A and then take the transpose. Now what does that mean? So question now reduces to, does the cofactor matrix make sense, right? Or does it make sense to define cofactors now when you are over an arbitrary ring? Well, what is the cofactor of an element? Suppose I have a matrix A And what's the cofactor of the ijth element? Well, I just look at, so ith row, jth column. The cofactor of this element is obtained by deleting the ith row and the jth column, looking at the remaining matrix, that's n minus 1 cross n minus 1, taking its determinant and then multiplying it by a sign, right? So that's exactly the ijth cofactor. So recall that cofactor of the ijth element of A is nothing but determinant of this matrix in which you delete the ith row, jth column, and then you multiply it by a sign, right? There is minus 1 to the I plus j. So this entire definition makes perfect sense, even if A has elements from a ring R, right? Because all I am doing finally is computing the determinant of some n minus 1 cross n minus 1 matrix, and I can compute determinants of matrices or any ring of any size. So this makes sense. So this is well defined, right? This is in fact defined. It's an element of R again. Sorry, not the cofactor ij is an element of R. Okay, the cofactor matrix means for every ij I put the cofactor of ij. Okay, so this entire definition makes perfect sense. And so what do I get finally? The adjoint of A is in fact a well defined matrix defined in the same manner with elements in R. Okay, and now the question really is, if I take the product of A and B, then do I get the identity matrix, right? And similarly the product of B and A. Okay, now let's just do one computation, just check one of the rows and all the other rows are similar. What do I get when I multiply AB? If I look at some, say the first row of the answer, so 1 comma jth element here, what does it look like? Well, it is by definition A1k bkj. Okay, this is a sum over k. So what is B? B, remember, is the transpose of the cofactor matrix multiplied by the determinant. So what is bkj now? So I need to say this is k goes from 1 to n, A1k. So what is the B matrix? B is nothing but det A inverse cofactor transpose. So the kjth element here is the cofactor of the jkth element. So this is this into cofactor of the j comma kth element of A, okay, because of the transpose, and then there is a sign, that's minus 1 to the j plus k. Okay, and then there is of course a det A inverse. So remember, all this is multiplied by a det A inverse, and since anyway everything is a commutative ring, I can multiply things in any order I want. So I will just put the det A inverse outside. So this is determinant of A inverse, this is a sum over k. Okay, now comes the important observation that A1k cofactor of jk. Okay, so if I put j equals 1, so remember j and k here, so sorry, j is variable, I can choose j as I want. If I put j equals 1, so when I take j equals 1 versus j not equal to 1, it's two cases. If j is 1, this is just going to be the cofactor of the 1 comma kth element of A, right? So let me just for the moment think of it. If j is 1, then this is the cofactor of the 1 kth element. This is A1k, right? And I am summing over k. So what does that mean? It's like saying that I take this matrix. So let's just draw this matrix here again. So suppose this is my matrix A. I am running through the first row, the entries of the first row, right? A1k as k varies, A11, A12, A13 and so on. I am multiplying each element by its corresponding cofactor, because this is exactly the cofactor of that element. And the cofactor just means I delete that row and column and look at what's left. But that's exactly how you compute the determinant of a matrix by expanding along the first row. Okay, so when I take j equals 1, this sum here turns out to be exactly the answer is exactly determinant of A, because of how the determinant can be computed by expanding along a row. and outside, remember, I have det A inverse, right? So det A inverse into det A, so this answer is just a 1. Okay. Now what about the other guy? Suppose j is not 1. What does that mean? It's like saying I take the entries of the first row, okay, these blue dots here, and I multiply them with the cofactors of some other row. Okay, j is different from 1. So for example, let's say j is 2. So I multiply these blue dots with the cofactors of the brown dots. Okay, so I do it along 2 different rows. Now the point is that expansion is well, what does it mean to take the cofactor of the brown dots? Every time I compute the cofactor of a brown dot, I will have to delete that second row and the corresponding column, right? That's how the cofactors of the elements in the second row are computed. Okay, so the point is that this answer now, for if j is 2 here, this answer will not depend on what those actual values of the brown dots are. Okay, so what I'm concluding, so this is the main argument. I am multiplying the values of the blue dots here with the cofactors of the brown dots here. Okay, now since every time I compute the cofactor of a brown dot, I will have to delete the row there, so I will have to delete the second row each time, and only the remaining elements will be part of the calculation. So this final answer here doesn't depend on what the entries of the second row are. It's the same answer for all possible choices of second row. Okay, now that's a very useful thing to know, because here's what I can do then. Since the answer doesn't depend on the second row, I can make a convenient choice of second row. So let me do the following. I will just make the entries of the second row equal to those of the first row. Okay, so let's make this choice. I now modify my matrix. I take the new matrix whose second row entries coincide with the entries of the first row. By the argument we just gave, this sum here doesn't depend on, so it will give me the same answer even after I have done this modification. Okay, now let us see whether it makes sense. So now what am I doing? I am computing the values of the blue dots above with the cofactors of the corresponding blue dots below. But since I have chosen these numbers to be the same, okay, each dot above is equal to the value below it. Now this sum has a meaning. I can make sense out of this sum. This sum is just the determinant of this new modified matrix when expanded along the second row. Okay, because I made both blue dot values the same, so I can think of it as I run over the second row, take each blue dot, multiply by its cofactor, take a blue dot, multiply by its cofactor, and so on. And when I make, do that summation, that's exactly the determinant when I expand along the second row. So this is therefore going to give me determinant of A inverse, that's still outside, times determinant of, let me call this A hash, this modified matrix. Okay, now what was this modified matrix? It was obtained by making the entries of the first row and the second row the same. Okay, but now we know the answer to this, because when two rows are identical, then the determinant must be 0. Right? That follows from the fact that when I interchange two rows, the value becomes negative. So in this case, therefore, I have obtained that this is 0. Okay? So what does that give us? We have finally proved that this product AB, when I look at its 1, jth element, it is 1 if j is 1 and 0 otherwise. Okay? So you can repeat the same sort of argument, replacing this 1 with any other row I. You can replace with any row I, and then a similar sort of argument works. So what we have really shown is that only when j equals I, you will get 1, and if j is not equal to I, you will get 0. So this argument actually shows that the product AB is identity, and you can just repeat the same thing in the other order. Okay, that corresponds to expanding along columns rather than expanding along rows. So you just have to repeat the same argument. So in some sense, what this does is really copies the same proofs that work in the case of fields, by realizing that you really aren't using the property of fields anywhere. it will work perfectly well over any ring, any commutative ring, provided that 1 by determinant A, that's the only catch. Provided that term makes sense, then you're okay. Okay, so this is a very important sort of statement, that a matrix over a ring R is invertible if and only if the determinant of that matrix is a unit in the ring. Okay, in particular, that example that we gave initially, this matrix A, which is 2 0 0 1, the determinant is not a unit in Z. This matrix is not invertible in M2 of Z. Okay, so here's our little corollary, that if I take this, so observe this example that I gave in the beginning, which is the matrix 2 0 0 1, is not invertible. In the ring of matrices with entries in Z. Okay, it's invertible if you think of the ring R as being the rational numbers or Q and so on, and in some sense you can see, it is invertible over Q. It's invertible as an element of M2 of Q, and in fact if you sort of use the usual way to compute the inverse, it's 1 by determinant of A into the transpose of the matrix of cofactors, which in this case is this. So here's the inverse, okay, by the usual formula for computing, and you can notice that, well, these entries aren't in Z, so this is half 0 0 1, that's the inverse, right? So it sort of ties up that you can invert it over Q, but the inverse will not have integer entries, it's going to have some denominators. Okay, so this sort of theorem is very important, and let's end this with a very important proposition, which is a corollary of all this analysis with determinants and so on, which says that if I have a free module Rn, okay, so this is all, again, everything we have said is only when R is a commutative ring. So if R is a commutative ring, then the free module Rn is isomorphic to the free module Rm if and only if n equals n. Okay, so this is of course one of the statements we would like to have, that the vector spaces have this nice notion of dimension, and a vector space say over the complex numbers Cn and Cm are two different vector spaces if n and m are different, right? The dimension is n, and we would like to prove something similar. It turns out we can really only prove it in the case of commutative rings. It's not true in general, and for commutative rings the proof sort of proceeds via determinants. So let's give a proof of this. So what does it mean to say Rn and Rm are isomorphic? It means that there is a isomorphism between them. In other words, there is a homomorphism phi which admits an inverse. So in other words, there are maps in both directions such that phi psi is the identity. So phi psi is the identity on Rm, and psi phi, the composition in the other order, is the identity on Rn. Okay, and again, as we have been doing throughout, it's best to convert everything to matrices. So let's give the matrices names. Let A denote the matrix of phi, B denote the matrix of psi. Okay, so one of them is, so let's see what the sizes are. This is an m cross n matrix. Okay, A is m cross n and B is n cross m. Okay, so we need to prove that m and n are equal, so we'll just make an assumption. So suppose m is the smaller of the two. Okay, we can repeat the same argument for the other case. Suppose m is smaller than n. Okay, now if m is smaller than n, so what was A? A was the smaller, so let's go up there. M is the smaller number, so that means that A has fewer rows, more columns. B has more rows and fewer columns. So what does A look like? Therefore A looks like this. A is m cross n, so it's got some m rows but lots more columns. It's a rectangle of this kind. B is sort of the opposite. It's got lots more columns and fewer rows. Sorry, lots more rows and fewer columns. Okay, so this is m cross n, this was n cross n. Okay, so now the claim is that, I mean, what we are saying really is that when you multiply these two matrices A, B, you will get m cross n matrix, m cross m matrix, that's also the identity, and BA is also the identity, right? So that's really what these two equations mean in terms of homomorphisms. The same thing here implies that, so we know the following, that when I multiply AB, it should give me a m cross m matrix, so it's the identity m cross m, and when I multiply BA, it should give me the identity n cross n. Okay, the claim is that this really can't happen. When you multiply two such rectangular matrices, both can't give you the identity. Okay, specifically we claim that this can never happen. Okay, the larger one can never be the identity matrix. So let's prove that. So claim is this cannot happen. Okay, so claim BA can't be the identity. Okay, remember n is a larger number, so the larger identity matrix, that can never happen. Okay, so let's try and prove this. Maybe we'll just do it sort of by example with sizes. So let me just take B to be 3 cross 2, for example. So B has, I mean, you can make this into a general argument too. So suppose B looks like this. B is say 3 cross 2. Okay, and then I multiply it by A, which is 2 cross 3. 3 columns, and okay, now I claim that this product can't give me the identity, right? So let's see, I want this, suppose it gave me the identity. Where's the contradiction? So suppose I got this, so they're all ones. Okay, suppose I had this, where's the contradiction? So let's do the following. So let's observe. So let me just move this over. So let's say this is the answer. Now let's do something to this matrix. Let's make B and A somewhat bigger. Okay, so I'm going to make, instead of B, I will put one additional row. Okay, so let's do the following. So let's move these over. So make some more space for B. So I'm going to augment B now as follows. So I will put an additional, so I'm going to make both of them into square matrices. So I have augmented B. Okay, so this new augmented matrix I'll call B hat, and A I will augment by just putting zeros on the bottom. Okay, this is A hat. Okay, so let's see. I claim that the same equation holds. If BA is identity, so if BA is identity, then I claim that B hat A hat is also identity, where B hat and A hat are just the augmented matrices. Okay, so I made both n cross n. Why is this? Well, just observe what the definition of how would you have done matrix multiplication. Well, you take the entries in the first row of B and multiply them by the entries in the first column, right? Now that multiplication, what will it do? What is the difference when you went from B to B hat and A to A hat? Well, it has that, that multiplication involves one extra term, which is this 0 into the 0, right? These two blue zeros are extra, they weren't there initially, but they don't contribute anything to the sum, right? It's just a 0 anyway. So it's only the original two red dots multiplying with the original two red dots that matters. What I have added extra is just a 0. So the answer here doesn't change, it's still a 1. Okay, similarly look at the second, for example, the next entry. The first row of B is multiplied by the entries of the second column of A hat, and the only additional term I'm introducing is this 0 times this 0. okay, and that's again no contribution. So it's only the original red into red plus red into red that matters. So originally the answer was a 0, right, because B into A is identity, therefore the same answer holds, it's still identity, I mean it's still a 0, and so on. So you just try doing this to each of these to each of these 9 multiplications you will have to do, and you'll notice that really you are not adding anything new, it's just the same answer as before, okay, with the 0 tagged along. Okay, so that means that if BA is identity, then the augmented matrices B hat and A hat also give product identity, but observe that both B hat and A hat have determinant 0. Right, now I am in the square matrix case and I can compute determinants. Now observe, determinant of B hat A hat must actually be the determinant of the identity matrix, which is 1, but we know that this is determinant of B hat, determinant of A hat, well, both of which are 0 because we explicitly put one 0 row or 0 column into both. Okay, so that's the end of the proof. That's a contradiction, right? You cannot have BA equals identity, means that you can't have M less than N. Observe, by the way, in this case that AB could be identity. If you try doing the same proof with AB, you won't be able to construct a contradiction. Okay, it's only BA that breaks down. Okay, so that's the end of the proof, because we have shown that M less than N gives rise to a contradiction. If N is less than M, then you do the other order. Then you show that AB cannot give you the identity. Okay, so this is an important statement. So what this proposition proves is that Rm and Rn can be isomorphic if and only if N and M are the same. Okay, and this involves the assumption that R is a commutator.